Okay, so the recording is started. So, yeah, I think we can get started. So we're very pleased to have joining us today, Rhys Steele from MPI Leipzig, who will be speaking about recent progress on BPHZ theorems and regularity structures. So go ahead. Yeah.
Yeah, yeah. So thank you for the introduction, and thank you to the organizers for the opportunity to give the talk. So I'm excited today. I want to tell you a story kind of evolving over the last couple of years on the probabilistic side of regularity structures. So as is kind of a common theme in rough analysis, in regularity structures, there's this split into a kind of deterministic solution theory that takes as input certain enhanced stochastic objects. And this is going to be a talk about the construction of those stochastic objects. Maybe I don't want to start by assuming everyone is 100% familiar with regularity structures and knows every detail of this. So for those of you who do, please bear with me a little while. I want to start with just kind of a gentle introduction that hopefully kind of gives you an idea of what the stochastic objects are that I'm going to be talking about in the rest of the talk. Of course, okay, my slides lag a bit, but I think that's fine. So of course, regularity structures is something very general. It treats a very wide class of equations and gives you kind of a short time solution theory basically for all of them. Let me start though much more gently. So I want to start just by picking a very simple example, maybe the simplest one that I can, which is the parabolic Anderson model in 2 dimensions. And I want to just give you a kind of very brief couple of minutes overview of what regularity structures does in the setting of this equation. So to try to pull the stochastic objects out of it. So what's the setting here? So the setting is that I want to look at this kind of PDE in 2 spatial dimensions, where this driving noise should be a noise that is white in the spatial directions and is constant in time, meaning in particular that it's of regularity just worse than -1. So you don't expect the solution to be of regularity better than 1, since the heat operator improves you only by 2 degrees when you take the inverse. And therefore, the kind of objects that appear on the right-hand side have a regularity that sums to something negative. So in some sense, eta is too oscillatory on small scales to be controlled by the local flatness of u on small scales. Therefore, this product need not deterministically make sense. So the kind of story of regularity structures is that in order to make sense of kind of these equations, and in particular, these kind of products on small scales, you need to somehow use the specific structure of the equation in a more specific way than just looking for u to be in a certain Hilbert space. So you need a better local description, maybe based, for example, on the structure of the driving noise eta. And this, of course, you can do. I mean, for example, in this equation, you can try to freeze coefficients. So you can try to insert a better local expansion on the right-hand side by saying that if you want to get this product to vanish to better order, it's, for example, a good idea at first to use that u vanishes nearly linearly, near to a base point z. So you can add and subtract everywhere this term u of z. And that's going to give you a better description of this product. So it's still diverging, but maybe now if this blows up at rate 1 and this vanishes at nearly rate 1, this is kind of blowing up only marginally. The cost is that I introduce an error term on the right-hand side, but this is something completely explicit. So this is some constant, and here's just a distribution on which I can certainly invert the heat operator. And by doing so, I can move it to the left-hand side of the equation, which yields me a more detailed local expansion of the solution. So that's what's kind of been done going to the 3rd line here. So I've introduced some notation. I use this lollipop just to denote the solution of the heat equation with this white noise on the right-hand side. Since that's an object of regularity basically 1, and I want to get good local descriptions, maybe the right thing to do is actually not to just introduce the lollipop, but also to recenter it around the base point z so that it vanishes to the right order. And in this case, I also smuggle in a polynomial that I'll mention in just a moment. Why is this a good idea? Well, now since this right-hand side vanishes basically or blows up only marginally near the base point z, so it's kind of at rate 0 minus, I might hope that PDE theory will yield, if I can make sense of the right-hand side, that the left-hand side is actually vanishing at nearly rate 2 near to the base point. That means in particular that I can use now this local description plugged into the right-hand side in order to get a description actually of this product that's going to vanish to positive order. So this I can kind of iterate. So I add and subtract the terms that are needed to make this kind of expansion appearing on the left appear also on the right. And now I get that every term that appears on the right-hand side, at least formally, is going to be vanishing to a sufficiently large order near to z that maybe I can control it, and therefore all of the remainders could be controlled via PDE techniques. And that's, okay, very quickly, because I don't have time to do regularity structures in detail, the basic philosophy of regularity structures. You look for good local expansions that involve kind of not just what you would see in Hilda spaces, so not just polynomials. Instead, you kind of involve these explicit stochastic objects that you have to build from the driving noise in an equation-dependent way, and you hope that you can get a description to high enough order that everything can actually be controlled by PDE techniques. What's the cost? The cost is that, of course, there are products here that are still ill-posed. So, for example, I have to take the product of this lollipop with the distribution eta. This is of regularity just worse than 1. This is of regularity just worse than -1. So the problem of taking ill-posed products still remains, but now it's been moved to a problem in terms of explicit stochastic objects. So that's something that I can hope to make sense of. And that's somehow the probabilistic problem in regularity structures that I'm going to want to try to tackle in the rest of this talk. Maybe let me start by asking how hard is that problem in general. So, of course, in the equation I just showed you, maybe it was relatively easy because there was essentially only one stochastic object that I needed to make sense of. In general, of course, there might be typically very many. So, for example, if you look at the KPZ equation in one dimension, so where your nonlinearity is a square of the derivative of your solution, already there are 5 of these stochastic objects that are potentially in need of renormalization, where if you haven't seen it before, I'll explain this tree notation a little bit more in just a moment. If you look at phi 4 in 3 dimensions, so where your nonlinearity is a cube of the solution, you will also need 5 trees. But as you make things more complicated, so for example, you look at the one-dimensional multiplicative stochastic heat equation, or the 3D generalized parabolic Anderson model, for example, there are already 9 stochastic objects. If you go more complicated again, so you look at the equations for the evolutions of Brownian loops on a manifold, there are, even after symmetry reductions, over 50 of these stochastic objects. And if you modulate the covariance of your driving noise to try to make it worse and worse in regularity, so you approach the critical threshold, it could be that there are arbitrarily many of these stochastic objects that you need to construct in order to have everything you need for the kind of pathwise solution theory that regularity structures would yield. So that's the problem that I want to tackle in this talk. In general, how can we construct, or how well can we construct, the set of stochastic objects that are needed as input in regularity structures, not for a particular equation at a particular regularity, but kind of as a general toolbox to input into the solution theory. So maybe let me kind of summarize that in what I'll call a BPHZ theorem. So a BPHZ theorem for me is the task of constructing this equation-dependent set of stochastic objects that I'll call the model. So that's the name it goes by in regularity structures. Typically, this will involve making sense of ill-posed products. In order to do that, well, I'll do what basically everyone does. I'll regularize the driving noise, for example, by mollification, so that everything makes sense. And the task is to pass to the limit the resulting objects as the mollification scale goes to 0. And of course, I need to do that in a way that is compatible with the PDE, in the sense that these stochastic objects should be related to the operator and the nonlinearity. What does that mean? So it means in this tree notation, whenever I draw a downward line, that should basically be the same thing as solving the differential equation. So for example, with the heat operator, modulo smooth functions that account for these recenterings that I was doing earlier, and maybe also the fact that I want to cut off, say, the large scales of the Green's kernel of this operator, but that I'll sweep under the rug. And also when I kind of look at the nonlinearity, so I might, for example, have to take products, which I'll denote by joining trees at the root. So for example, for the one tree that we saw in PAM, I might write this dumbbell symbol, which would be morally the same thing as taking a product of my noise, which I denote by a dot, with this lollipop that you saw earlier. And this I should want to do at fixed epsilon modulo a suitable renormalization so that things can hope to stay stable in the limit, which here means I might have to subtract off an epsilon dependent constant, which may be diverging as I send epsilon to 0. And the goal is to do all of this in such a way that these things are not just stable as distributions. In fact, for the analytic theory of regularity structures, you need a little bit more. Namely, you need a certain order bound. So you need to know that you constructed these distributions in such a way so they're base point dependent, because repeatedly I had to recenter things. And I need to know that if I probe them at their base point at a length scale lambda, then at least in pth moment, they should vanish or blow up like lambda to this absolute or value or degree of tau, where this thing is defined by saying that for example, the degree of my noise symbol should be just equal to the regularity of my driving noise. If I integrate, that should be like inverting the heat operator. So I should improve regularity by 2. And if I take a product of two trees, then that should be like summing the two quote unquote regularities. And maybe let me point out that this last condition makes this assumption much more stringent than just looking at these objects as just distributions, since if you multiply two distributions, it's typically not true that you get the sum of the two regularities. This you can already see at the level of Hilda functions. So this is something that comes because I have the base point dependency. So it's something that's more like multiplying the increments of two Hilda functions around the base point x, where you will get the sum of the two vanishing orders as the resulting vanishing order around the base point. So that means in particular that the task that I have is not just controlling these things as distributions, but rather in a much stronger topology. And constructing everything in a way that these things remain stable as epsilon go to 0, and such that you have convergence in the corresponding topology. That's what I would call a BPHZ theorem in regularity structures. Okay, if you didn't see it before, maybe that's a lot of information at once. I'll give some explicit example of one of these trees later where I actually do some computations so you can see this a bit more in practice. Maybe for now, though, let me kind of tell you a bit the history of these theorems, because it's of course not true that these are things that have been proved recently for the first time. So in fact, the first proof I would say of a kind of very general result in this direction is due to AJ, who's in the audience, and Martin Heire now 10 years ago. Okay, of course, there are people, including AJ, who understand this better than me, but I tried to summarize what I understood. So I would say that this is a proof of, a BPHZ theorem by viewing the problem of getting these kind of estimates as really a problem to do with iterated integrals. So if you think about the recipe that I gave you on the previous slide for constructing these objects, it was built via iterated convolutions of the Green's kernel with your noise and iterated instances of taking products. So that means you can write this thing as some big iterated convolution of your noise with various instances of the heat kernel. If you then take this as being p copies of that iterated convolution, and maybe you pull the expectation inside, and you know the cumulant structure of your driving noise, what that means is you can equivalently write this bound as bounding some explicit iterated integral that depends on the Green's kernel of your operator and on the cumulants of your driving noise. And what AJ and Martin were able to do, very kind of briefly summarized, is show that you can design a multi-scale algorithm where you break up every part of this iterated integral into its kind of components at dyadic length scales. And for each possible way of assigning the dyadic length scale, you can find a way of either harvesting the correct renormalization constant or the correct recentering in order to get the right stochastic estimates for this uniform bound and the corresponding convergence statement. Okay, that's a very brief summary. The reason it's very brief is actually these iterated integral methods are not going to be the main topic of the talk. And in some sense, the reason is that they are, I think, necessarily sufficiently notationally complicated just because of the number of objects that are involved, that by the time you put more generality on top, they become very hard to work with. So the reason I'm able to give a talk instead on recent progress on BPHZ theorems is in the intermediate time, so roughly halfway between 2016 and now, there was a new approach to proving these kind of BPHZ theorems in regularity structures. So this comes kind of in December of 2021, which is in a paper due to Pablo Linares, Felix Otto, Marcus Tempelmeier, and Pavlos Satsoulis. So actually, they work in a slightly different variant of regularity structures called the multi-index setting. Roughly speaking, this is a kind of more intrinsic approach where you try to describe only the solution of the equation rather than all of the distributions that would appear in a fixed point problem. And by doing that, they kind of lost access to the iterated integral techniques that AJ and Martin were using. So they needed a new perspective on how you could obtain at least uniform bounds on the renormalized objects that you need to construct in order to apply the kind of regularity structures machinery. And I think they came up with a quite nice idea coming from stochastic homogenization, which is that you can use Malievan calculus in a quantitative sense in order to obtain stochastic estimates. And that's in the form of this spectral gap inequality. So what that tells you is that you can bound a sufficiently nice functional of your driving noise in peak moment. So say, for example, the model is my favorite function of the driving noise. In order to bound it, if your underlying noise satisfies this spectral gap assumption, it's sufficient to bound the expectation and the pth moment of the Malliavand derivative, which here I've written for convenience just by duality as really being the directional derivative in a direction g, where I then have to take a supremum over g in the unit ball of the Cameron-Martin space. So for example, if your underlying noise is Gaussian, it will satisfy a spectral gap inequality. And if it's, for example, a space-time white noise, it will satisfy a spectral gap inequality where this space H is L2. Why is that something that's useful? Well, it's useful for kind of two reasons. Firstly, you obtain a kind of natural monotone parameter with respect to which you can try to count your stochastic objects inductively. So rather than thinking of them all separately, you can try to say that by taking a directional derivative, I really reduce the number of instances of the noise appearing in my stochastic object by one. So maybe this is well described in terms of objects I've already seen earlier in an inductive proof. On the other hand, you also manage to gain something else. Namely, you can do kind of the opposite of what embeddings will usually do for you. So usually you can give up regularity to gain integrability. In this case, you manage to do the opposite. That is, you take an instance of your driving noise, which is typically of low regularity. For example, if it's white noise, it's of regularity minus dimension over 2. And you manage to replace it by an element of the Cameron-Martin space, which in the case of white noise would be something like L2. So you gain 5 over 2 degrees of regularity. That means the hope is that you can make sense of these kind of things deterministically, even if the object appearing on the left-hand side by power counting is ill-posed. And this is the kind of basic idea that this paper took in order to obtain uniform bounds for the model associated to a particular quasi-linear SPDE in this multi-index setting. So on the one hand, that's a very nice observation. I think it's beautiful that we have kind of a new tool in order to estimate stochastic objects that would appear in this kind of setting of singular stochastic PDE. On the other hand, this result is much less general than the result of AJ and Martin, since it applies to a particular equation, it bounds a linear set of stochastic objects, and it doesn't obtain the corresponding convergence result. Nonetheless, these are all things you can do. So actually, just over a year later, so in kind of January 2023, I had a paper with Martin where we adapt this spectral gap approach to the tree-based setting, obtaining both uniform bounds and convergence, so a result of analogous generality to that of AJ and Martin. And we develop also some new analytic tools to control the Malliavand derivative, and those I'll try to show you in a very special example later to make all of this concrete. Of course, there's kind of many more works in these years, so let me kind of finish the brief summary. Within 2023, people were, for example, able to adapt this paper to treat other equations like the stochastic thin film equation, that's here. They were able to obtain convergence also in this multi-index setting by the same argument that Martin and I used. And they were able to adapt it also to treat the phi-4 equation in the multi-index setting using kind of the analytic tools that were developed in this paper. Furthermore, there was an alternative kind of a proof of a result at the level of generality of either of these two papers due to Ismail Bayol and Masato Hoshino using completely different analytic tools to the ones that were developed in this paper with Martin. So in some sense, the kind of takeaway from this, that's a very brief literature review. The thing you should, I think, take away is that, of course, the spectral gap inequality is somehow a useful tool. I described maybe why at a high level. Maybe more importantly, though, somehow in these periods of years, there was a very large burst in understanding of these BPHZ theorems in regularity structures. And the goal of this talk is to try to give you a brief impression of what that understanding is, and maybe also how it's been leveraged in kind of the years following 2024 to obtain generalizations of what you could do with regularity structures before. Okay, but maybe let me start by, this was all very high level. Let me start by trying to make things more concrete. So I want to show you in a concrete example why spectral gap is actually useful to obtain stochastic estimates. And that I want to do in, again, the simplest example where you can really kind of see what regularity structures is doing, which is just the example that I had on this first slide. So I want to try to treat this first tree in the parabolic Anderson model using the spectral gap approach. Of course, this is something you could do very easily by writing things with iterated integrals. So for those of you who've seen this before, what you see here might look more complicated. The advantage is basically all of the analytic ideas that I would need for the kind of very general proof are contained in some form in this example of the most simple tree that you can think of. So this kind of approach generalizes much more well. So what's the task? So let me first recall that, this distribution is something in this case I can write very explicitly. So I want to take the product of my white noise and the solution of the heat equation driven by the same white noise. And then there should be, of course, a recentering. So that's the recentering that I put here, and it's the same one that appeared kind of on the first slide. So remember there I wrote, I think, something like this, which is the same thing as I've written here, just now made more explicit. And there should also be an appropriate renormalization. So I have to subtract off some constant to kill the expectation of this term. And the goal should be that if I convolve this with a test function at scale mu, and I look at the same base point here and here, then I get a bound that's just worse than mu to the 0. So you should think this kappa is an infinitesimal parameter. How am I going to do that? Well, I have kind of only one tool. It's the spectral gap inequality. So I'm going to do it by taking a Maliovan derivative. If I do so, I can compute things explicitly. So, I mean, first of all, this constant is, of course, killed by the Maliovan derivative, since it doesn't depend on the realization of the noise. On the other hand, in these terms, I have a product of two instances of the noise. So by Leibniz rule, I'm going to see two contributions to this directional derivative, one where the derivative hits here and one where it hits here. And so that's the two terms I've written down. Now maybe I want to cheat just a little bit. So actually, this second term would be notationally a bit more complicated than the first term, essentially because there's going to be a step in the argument where I have to add and subtract the right kind of Taylor jet. So here, this base point recentering is going to be wrong. That's going to be slightly more involved for this second term because this is an object of regularity nearly 2. So I would have to see also an affine term in the Taylor jet that involves kind of the gradient. That's just notational complexity. One can do it, but let me kind of skip that so that I can get through things more quickly and just focus on this first term. I'm also, for simplicity, going to pretend I can ignore the expectation term that appears on the right-hand side of the spectral gap inequality. So if you remember on the right-hand side, I had to bound both the expectation and the Maliovan derivative, and I'm going to pretend it's enough to just bound the Maliovan derivative because I think there you can see the key ideas. And so that leaves me with the task of bounding, of just showing that this term, when convolved with phi mu and evaluated at x, goes like mu to the minus kappa. Okay, so that's what I say here. So let's try to do that. Well, actually here the goal is to make, it's going to be computational, but the hope is that I can make it computational in kind of a soft sense, in the sense that I can kind of ignore by now all of the structure of my noise other than its regularity. So I hope I can just remember that this object is of regularity just worse than 1, and the fact that I've been able to take a Maliovan derivative is all the probabilistic information that I need. And it turns out that this is correct, so let me do that. Let me set h epsilon to just be this convolution, and I'm just going to remember that h epsilon is of regularity just worse than 1 in the Hölder sense. So the thing that I want to bound is then this term. I've just copied over from the last slide the thing I wanted to estimate. And now I want to estimate it in an L2-based way, ideally, right? Because this G, remember, is an element of the Cameron-Martin space for white noise, so this is an element of L2. Unfortunately, here is not something in L2, so I have to cheat a little bit more. I want to pretend that my test function has the convolution semigroup property. You can think, for example, of the heat kernel, or if you want to put something compactly supported, it's a little cheat. You have to not use one test function here, but 2. But please believe me, that's kind of very minor using standard analytic ideas from kind of harmonic analysis, let's say. It's not so deep to do this. So that means I can, let's say I can cheat. I can replace this test function by really its convolution with itself. That's all I've done to pass to this second line. Why is that helpful? Well, now I hope that I can use the Cauchy-Schwarz inequality to put an L2 norm on this guy and an L2 norm on this guy. And then I'm in good stead because I'm estimating this thing in the right kind of topology in terms of integrability. If I do that, things are nearly perfect, except this base point is the wrong one. So the key idea is that I then need to kind of add and subtract the right term to make the base points here and here match. And that I can easily do. So I just add and subtract h epsilon of y and apply the triangle inequality. And now in order to control this Maliovan derivative, I have to control only 2 terms. So maybe let me do that on the next slide. So, okay, first, by applying Cauchy-Schwarz, I can put an L2 norm here and an L2 norm here. And I'm almost entirely going to forget about this extra test function that I smuggled in. The only cost is that it's scaled in a way that keeps its L1 norm independent of mu, and I'm taking an L2 norm, which means that this thing really scales like mu to the dimension over 2, which in this case is mu to the 2 over 2, so this is mu to the minus 1. So in both cases, I'm going to pick up a mu to the minus 1 that comes from the L2 norm of this test function, And in this second case, I'm actually going to gain something back because this, remember, was almost of regularity 1. So this goes almost like y minus x, and y minus x is basically of order mu, thanks to the support of this test function. So I'm going to gain back in the case of I2 almost a whole power of mu, which will almost entirely cancel this mu to the minus 1. So that means for I2, by applying Cauchy-Schwarz, I get a bound that's like mu to the 0 minus, which is what I want, times the convolution of g with phi in L2. And for I1, I have this power mu to the minus 1 that I still have to kill. Okay, first, what's going on here? I mean, this is very easy, right? G is in L2. This is in L1, uniformly in mu. So this is just Young's convolution inequality. There's almost nothing to do. This goes like mu to the 0 minus. On the other hand, for this second term, I have to work a bit harder. So if you ignore this kind of recentering, you would have a product of something in a regularity 1 space with something in a regularity 0 space. And so that would typically really vanish only like mu to the 0, which would be much worse than what I needed. Thankfully, this is not just that product, it's really a commutator. So here I have one term where I first multiply and then convolve, and another term where I first convolve and then multiply. And I think it's a very well-known fact for many areas of analysis that these commutators tend to behave better than just products alone. So typically you don't get kind of the minimum regularity, you in fact get the sum of the two regularities, which here is something like 1 minus and 0. So here you can expect a bound like mu to the 1 minus by some kind of commutator estimate. For those of you who know a little bit about regularity structures, in particular who have heard of the reconstruction theorem, you might actually recognize that this is even exactly an instance of the reconstruction theorem. So this is something like the pi of f, and this first term is something like the reconstruction of f. So what's the takeaway? So that was maybe, a concrete calculation done quickly. I hope what you can glean from it, though, is that I was able to avoid, by using this spectral gap inequality, any very precise iterated integral calculations. So I didn't have to write down anything with exact equalities. I just needed everywhere very soft upper bounds for things. So this tells you that in some sense, spectral gap is a very useful quantitative tool for making estimates for stochastic objects look more like deterministic function space analysis. And that you can do because at the level of the Malievan derivative, you've gained enough regularity that the problem of renormalisation in some sense has gone away. On the other hand, there are actually several other takeaways that I think are important for the rest of the talk that are maybe less obvious. The first is that it's very helpful in these approaches to really view the stochastic objects you're looking at as built recursively, rather than viewing each as a kind of individual object. The reason is that, I mean, you saw already in this very simple example that I had to add and subtract the right Taylor jet, so I had to change the recentering. You can imagine if I have now a very complicated stochastic object with many instances of recentering inside it, this might be a very difficult task to do. On the other hand, regularity structures was built exactly as a calculus of local expansions that was meant to automate these tasks for you. So you might hope that if you work recursively, you can do exactly this kind of adding and subtracting of these local approximations in a systematic way using regularity structures. And that indeed turns out to be the case. So you can construct a variant of the spaces used in the solution theory, these spaces of modeled distributions, in order to obtain the required estimates. And maybe, okay, I briefly put them on a slide. The exact bounds here are not so important. You should view them as something like, if you forget the L2 norms, these are the usual bounds that you would require in the solution theory in regularity structures, except here I require that in an L2 sense, they have a certain vanishing as I send lambda, so the size of the ball I integrate onto 0. So you can think this is something like a regularity structures analog of Campanato spaces in classical PDE theory, if you're familiar with those spaces. If you're not, and these bounds are kind of very surprising to you, don't worry, I'm not going to use them in any way in the rest of the talk. They're just to put on the slide somewhere that you need to build some kind of variant of the kind of classical model distribution spaces for those of you who know a bit the details of regularity structures. So in total, that's a summary of kind of the progress we had maybe 3 years ago. The spectral gap inequality gave us a very useful new tool in order to obtain stochastic estimates for renormalized models. Along the way, we developed several new analytic ingredients that were useful also in obtaining those estimates. Now, maybe the question is, where does the story go from there? I mean, I called this a talk on recent progress. Depending on your timeline, maybe 3 years ago is not so recent. So kind of what comes next? And okay, maybe I check in. So I think I'm about halfway through. This is actually maybe a good stopping point for the break if we're roughly there. Is that correct?
Yeah, this could be a good stopping point. So yeah, thank you for that very nice overview, Rhys. Yeah, are there any questions from the audience? Um, yeah, I mean, maybe this is this is a kind of broad question, but what do you think about um, like how much does the spectral gap assumption limit you? So what's the kind of scope of like how should people think about the assumption? So there's, so Gaussian noises satisfy that. But what are the cases where you think that that's that's a kind of real limitation?
Um, so, I mean, in reality, I think in most applications, you are looking at very explicit Gaussian noises. That's maybe the first comment. I think for all of these BPHZ theorems, this is the real test case. So we write much more general assumptions, but we're really thinking of kind of, let's say, fractional derivatives or inverse fractional derivatives of a white noise. That's the usual case. And in those cases, the spectral gap assumption will apply with the Cameron-Martin space that you get by taking L2 and applying the right fractional derivative. So in that sense, I think it kind of does the thing that you want. More generally, I think it's actually kind of hard to exhibit a noise that you would see in practice that's not a Gaussian that would satisfy the spectral gap inequality. So of course, there are things that have this property, like we know, for example, like if you want to be crazy, the solution of phi4 has this property, but they're not things that you would usually put in a driving noise. So I would say the kind of good thing to keep in mind is Gaussians, but that's kind of, I think, standard as my experience is that's what you want to do in practice anyway. So for me, that's not such a limitation.
Okay. But so I guess sine Gordon is still completely out of reach of this method, or
Yeah,
is there
I,
some
I at
hope?
least I at least wouldn't know how to start with sine Gordon. Um, so my understanding, okay, I'm not an expert, but you do this de Prato de Buch trick once and you end up with these kind of complex exponentials, and these won't have spectral gap. And it's also not obvious that there's any way to use the spectral gap of the underlying Gaussian, I think, in this setting. I mean, that would be your only hope, and I wouldn't know how to do that. So I think sine Gordon is the kind of example where these iterated integral techniques are somehow much better than spectral gap.
Okay, thanks. Yeah.
So the spectral inequality is more like a sort of a Poincare inequality.
Yeah.
On the right hand side, the derivative is the Malevin derivative. Right?
Yeah. So I think that's fair. I would say it's Poincare and probability is, I think, a good tagline.
So this tells you how to. So after renormalization, after suitable renormalization, this tells you how to bound the moments in a recursive way. But
Yes.
this doesn't quite tell you how to renormalize. Say if
Yeah, that's a good question. So this I kind of skipped over in the hope to get to more recent things. So in the spectral gap inequality, I mean, I looked actually already in PAM only at one term on the right-hand side, this Malevin derivative term, and you'll notice that already the renormalization constant there just vanished. And it's actually true in general that once you control the stochastic objects to some order, when you want to build kind of the next one, if you're only interested in the Malevin derivative, you never see the need to renormalize, or at least under suitable assumptions on this kind of no variance blow-up condition that Mate was talking about. You can see as a kind of no Malevin derivative blow-up. So these are kind of deterministically well controlled. The way you see the need to renormalize is actually that these expectation terms can typically be diverging if you don't renormalize in a suitable way. So somehow you get a nice separation of the problem where all the renormalization is here, and this is somehow just deterministic analysis that doesn't see the need to renormalize.
So there's a question in the chat. in the definition of model, we require the P moment of the realized object to satisfy some inequality. How do we decide which P we use? What does it mean to choose that particular P?
Yeah, good question. So this is here. So I mean, typically the thing you're actually interested in when you do the solution theory is you want to work kind of pathwise, which means you would really like to kind of forget that this expectation was ever here and just assume that realization by realization you have this kind of bound. That means you want to use something like a Kolmogorov criterion to say that once you have bounds on sufficient moments, you can actually kind of pull all the supremum inside the expectation and get instead pathwise bounds. There are indeed bounds of this type, Kolmogorov criteria of this type also for models. And so in practice, what that means is you want to establish this kind of bound for sufficiently large P so that you get this kind of Kolmogorov criterion up to a very small loss. So you take P large enough and the loss that you make by Kolmogorov gets very small. And then you forget that the P was ever there at all. What that means when you run the spectral gap argument is typically that you want to kind of start with P large enough, that's your target P in mind, and then maybe when you're working recursively, you take a product, you have to apply Hilda, so maybe you need to change the value of P throughout this recursive argument. But that turns out to be not a problem because you have this spectral gap in basically every finite P up to the fact here that this constant may be P dependent. But since things are subcritical, I'm only ever constructing ultimately finitely many of these objects at a time, so I don't have to worry too much about the constant here. So at the end of the day, you can kind of think of this P for the probabilistic problem as some large enough constant that's certainly finite, and for the deterministic part, you forget it entirely.
All right.
So again about the renormalization, I mean, sometimes the renormalization is more complicated, like there might be nested subdivergences and so on. So I guess the renormalization not always subtracting the expectation. In that case, do you mean this inequality on the screen, in some sense, automatically unlock the subdivergences and so
on? Yeah, so I mean, in this approach, you somehow never see this problem of overlapping subdivergences. Like if no one told you it was there, you would never notice it. And so somehow I think the only way you see it is that you have to somehow check that the description, so you try to get a good local expansion of this Malievan derivative. You can, of course, guess what the right formula is, ignoring renormalization. And then you have to check that actually renormalization didn't destroy this thing. And this is where you see you might have subtracted something more complicated than just the expectation. But that turns out to be true in general. It's a kind of not so complicated algebraic check. Okay, it's not a short computation, but it's somehow entirely elementary. It's just substitutions in some iterated sums. So somehow I think that's one of the advantages of this approach, that this kind of quite complicated problem of overlapping divergences entirely disappears. You never run into it.
I had another question, which is that, so the kind of iterated integral approach you described, like multi-scale analysis of diagrams that was used as it's a kind of adaptation, with some changes of stuff that was used for Feynman diagrams. The spectral gap approach, it's very nice, and it seems to use kind of analytic structure as well. Is there, do you know of any work or any attempts to use this back in the world of Feynman diagrams? Because there somehow we don't really have the analytic picture, as far as I know.
Okay, so first, can I check, do you still hear me? Because I got a pop-up about my microphone not working. You do still hear me, good.
Yes.
Yeah, so no, the answer is no. I don't know of anyone trying to do this. I think it would be interesting. So somehow the story is this comes from a very different direction, from the corrector problem in stochastic homogenization. It's kind of made its way into renormalization via regularity structures, and as far as I know, not gone further than that. So it would be kind of interesting if you could push it also more in the direction of QFT, but I'm not, at least I don't know of any work doing this.
Okay. Are there any other questions before we let Rhys continue? And if you want like a 2 or 3 minute break, Rhys, we can do that. But if you're happy to continue, we can continue.
No, if it's okay, I would maybe take just a minute to go fill up my water because it's very
Sure.
warm in this room.
Yeah, go ahead.
Thanks.
So maybe we'll start at just 15 minutes before the hour. So at 45 minutes after the hour.
Sounds good.
Okay, so I think we'll get started. Yeah.
Um, one moment. So I notice you don't see. Let me maybe stop sharing and restart because I think I noticed on my laptop you see a different thing to what's on my iPad. So
I
one
see it.
moment.
Yes, the last thing I saw was a slide that said, "What did we learn?"
Yeah, and that should have changed. So now, yeah, now it looks like it's working better.
Good. Okay. What questions
Okay.
are left over?
Yeah,
Yeah, good.
good. Yeah, so maybe let me kind of continue actually by trying to briefly leave spectral gap behind. So of course, this kind of story with the proof of BPHZ via spectral gap is by now a few years old. So depending on your timeline, maybe it's not recent progress in regularity structures or in BPHZ theorems. So what I want to try to do with the rest of the talk is explain to you why I think these kind of probabilistic problems in regularity structures are still interesting, why there are things kind of left to do there, and what we've managed to do, what not. In order to do that, I need to know a little bit about what regularity structures can already do, So I want to try to give you just a high-level summary of actually what you get out of the machinery of regularity structures if you read all of the kind of long papers. So let me try to summarize the kind of what I would call the core meta theorem of regularity structures, which was established over the course of 4 papers written by subsets of this set of authors in various combinations. So what does that say? It says that if you have a sufficiently nice, let's say even system of singular stochastic PDEs, you mollify your driving noise at some length scale epsilon, then you can find a sequence of renormalization constants and some functions of your solution and maybe its derivative, in the case where here you put the heat operator, that don't depend, these functions don't depend on epsilon, such that if you look at the solution of the kind of corresponding renormalized PDEs, so you put here the kind of same nonlinearity, but where you mollify the driving noise, and you insert the correct counter term at fixed epsilon, then these solutions will actually converge to a non-trivial limit as epsilon goes to 0 in a suitable Hilda space. And furthermore, you can choose those constants so that the limit is independent of the mollifier. So if you look at things this way, I mean, it looks like there's not much left to do. At the level of kind of resolution here, you might think kind of every parabolic semi-linear equation basically looks at this form. So maybe there's nothing left open. That's because sufficiently nice is doing here really a lot of work. So there are, I think, actually quite a few assumptions hidden inside this sufficiently nice. I want to maybe spell them out a little bit to explain why I think that there are still questions left to ask in this setting of kind of subcritical parabolic equations. So first, here the assumption that the SPDE is sufficiently nice, of course, has to include regularity assumptions. I think this is well known. So regularity structures applies primarily to subcritical equations, primarily exclusively so far to subcritical equations. So I need to assume that kind of when I start doing Picard iteration, at every step I formally create objects that are of higher regularity than the ones I saw previously, rather than of the same regularity in the case of critical equations or of worse regularity in the case of supercritical equations. I would usually say maybe less well known in the direction of regularity assumptions is that I also need to assume that things are regular enough so that I avoid a certain phenomenon known as variance blowup. This, I think, fortunately for me, the last talk in this seminar series, Mate already explained variance blowup to you, so this I can kind of skip over. It basically says that every non-trivial object should have regularity better than minus dimension over 2, let's say, and that's the gain in regularity you make when you pass from a noise to the Maliovan derivative. So you can think that it means the Maliovan derivative always makes sense deterministically, if you think of the spectral gap assumption. This list of assumptions should also include that the problem is translation invariant, in the sense that the operator is a constant coefficient operator and the noise is translation invariant in law. So it rules out doing anything with kind of geometric features, in the sense that your domain has some kind of geometry. And it assumes, and for me, what's quite a strange assumption, that the way you approximate your equation is by mollification. So in some sense, you had to make an arbitrary choice. You had an equation that didn't make sense. In order to interpret it, you had to choose some way of regularizing it so that you could kind of do the renormalization and pass to the limit. And you made the arbitrary choice that approximation scheme was by mollification. But there's no particular reason why this is kind of canonical. So you might want to know that you can obtain the same solution via a much wider class of approximation schemes. So, okay, this is not all of the assumptions that sufficiently nice holds, but it is kind of a list that's relevant for the rest of the talk. So kind of the goal of the rest of this talk is to ask in each of these cases, can we relax these assumptions? What I want to do then is to try to give a summary of various works that are doing exactly that. And then maybe I'll zoom in on only one of them in detail. So I'll try to talk about this translation invariance assumption in a bit more detail than the others. So let's start there. I have another very quick, one caveat. When I'm removing each of these assumptions, I'm not brave enough to try to do critical things with regularity structures, so that's not going to happen in this talk. I'm just going to talk about these other 3. So one regularity threshold, one kind of translation invariance assumption, and one thing about mollification or approximation schemes. Okay, so what kind of work goes in that direction? Let me maybe start by mentioning that there's of course work that's not work of my own that does very nice things with the spectral gap inequality. So it shows that you can get much finer properties of the BPHZ model based on this spectral gap proof. So this is work from last year and this year. One work by Bael, Hoshino, and Takano that's able to show that if you assume a stronger functional inequality on your driving noise, that's a transportation cost inequality, then you can get the same property for the driving model. And thus, for example, Gaussian tails, even if you don't know the noise is Gaussian, and also in general, large deviation principles for your model. So this kind of generalizes earlier work in special cases obtaining large deviation principles for singular SPDEs. In addition, there's a work of Simon Gabriel and Markus Tempelmeier that's only now a couple of months old, I think, in which they show that the spectral gap inequality can be used also to obtain these weak universality properties for phi-4, meaning you look at an analog of the phi-4 equation where you replace the cubic term by a more general polynomial, you multiply by the right power of epsilon for each term so that you should see only the cubic term in the limit, and they show at the level of the model that in the full subcritical regime, even with long-range driving noises, you're able to obtain these kind of weak universality results. So that's a kind of significant generalization in terms of kind of regularity parameters of what people were able to do previously in special cases. In addition, spectral gap, let me very briefly mention, so this is work in progress still, but mathematically I think mostly kind of done, just long progress of writing up. I'm very confident that you can also use this spectral gap approach to treat a much wider range of approximation schemes. So that's a work in progress with Martin Heire, Shumei Li, and Francesco Padula, who was a PhD student of Martin and Shumei. And there what we're doing is we're showing that you can extend this spectral gap proof to also cover, for example, not just modification, but for example, space-time discretization, discretizations of just, say, space, and also, for example, let's say viscous approximations where you regularize by just perturbing your operator by a higher order part. The thing that all of these things kind of have in common is you can make a corresponding notion of Bezoff space that's well adapted to these kind of notions of regularization, and that's the kind of key analytic ingredient that goes into the spectral gap proof. That gets very technical very quickly, so I maybe don't want to go into details on it. Maybe I mentioned that kind of, yeah, so since he now left academia, it's good to mention, I mean, this is really a work that I would credit mainly to Francesco. So unfortunately, he now left academia, and that's kind of the delay in writing it up, since it's very technical to develop this very general Bezoff space theory that covers all of these discretizations at once. But mathematically, I think the result is there. So I would kind of claim that it's true you get a BPHZ theorem at the same level of generality as you had in the modification setting now for all of these kinds of discretizations. Yeah, good. Maybe that's all of the detail I want to give there. Let me briefly also scan over variance blow-up. Yeah, so usually I would go into much more detail here. I think it's a really interesting question, but since Mate already spoke about it, let me not do too much. So let me mention that there are there are various works that have tried to also push this regularity threshold. So they've tried to ask what happens when you don't have power counting such that the Maliev derivative is automatically well controlled. That's a phenomenon we understand via spectral gap much less. So in some limited examples, basically KPZ, either by inducing variance blow-up manually or by looking at rates of convergence, we understand things recursively using the spectral gap approach. If you look at something more nonlinear, like the GPAM, the generalized parabolic Anderson model, so far we only understand it using these kind of more diagrammatic techniques or iterated integral techniques. And so here I think there's kind of a big open question that we're much less general than this kind of BPHZ theorem that I think would be very well worth understanding, but we don't understand yet. But since Mate already spoke about this in this seminar series, let me not go into more detail. Instead, let me come to the setting that I want to spend the rest of my time on. So this is the last of these kind of generalizations that I didn't yet talk about. I want to talk about what happens without translation invariance. So this is going to be primarily about a work that went on arXiv last year with Luca Brooks, who's now at CISA, and with Harpreet Singh, who I think is maybe still officially. No. He's at ETH. He did already move. I wasn't sure. Yeah, so he's now at ETH. So what's kind of the question? The question I think is a very natural one. What happens if you drop this assumption of translation invariance? So for example, what happens if you replace your constant coefficient operator by a variable coefficient operator? From a PDE perspective, that seems like a very benign thing to do. I mean, it's very strange to have a PDE theory where you kind of understand very well the Laplacian and you can't put a small perturbation of the Laplacian. Unfortunately, from this singular SPDE perspective, it actually seems to be a very hard problem. So you can go through the entire of this spectral gap proof of BPHZ, line by line. You can work out where you crucially use the assumption of translation invariance, and you'll find that you used it actually only once when you were bounding this expectation term. So that seems kind of very promising. And then, okay, at least I spent several months hitting my head against that one line trying to improve, and I got really nowhere. And I think this is true actually for several other people also who wrote these spectral gap papers. So it seems like if you want to tackle these non-translation invariant problems, you need new ideas outside of spectral gap. And I think those are problems that are worth tackling, both because they're kind of natural from a PDE perspective, but also because they should kind of arise from a correct phenomenological perspective. Like we often write down kind of macroscopic physical models as singular stochastic PDEs, and the second you put any of these into a heterogeneous background, the natural way of understanding them would be that there is a variable coefficient operator appearing. So then if you want to understand how these things depend on the background you put them in, you should understand how sensitive they are to replacing your Laplacian with a different variable coefficient operator. So in the rest of the talk, I want to think about exactly that. I want to think about what happens if I allow my coefficients to depend on a space-time point. In particular, the goal, maybe let me say first, what do you expect? So what gets harder? Well, beyond the fact that the spectral gap proof seems to break, things get harder because you qualitatively change the equation. So this is why it's not like the classical PDE case, right? In the classical PDE case, your operators are a bit different, but it has roughly the same analytic properties. In this case, you change the way you renormalize. So since the equation is no longer formally translation invariant, it's just not reasonable anymore to expect that you renormalize only by constants. Of course, if you renormalize by general functions, that's way too many degrees of freedom, so you should restrict somehow. And it turns out that the kind of natural restriction, at least if you work at a very high level of generality, is that you should impose kind of translation covariance at the level of your renormalized equation, at least formally speaking, which turns out to mean that you should only allow yourself to renormalize by counter terms that are local, in the sense that they don't depend on the space-time point in an arbitrary way, but instead only via kind of finitely many derivatives of your coefficient field. So the goal for the work that I want to describe in the rest of the talk is to establish an analog of the earlier meta theorem. So this is mostly a copy-paste of what I wrote earlier with two changes. Firstly, I would like to allow myself to put here a more general form of differential operator to understand what happens when I have heterogeneous background materials. And as a cost, I can no longer renormalize just by constants, but I would like to understand whether I can do that instead by local functionals in the sense that they depend only on finitely many derivatives of my solution. And otherwise, this meta theorem is really the same. In particular, these functions upsilon are really the same functions upsilon that you would see in the constant coefficient setting. So if you happen to take the coefficients in these operators to be a constant, so that this is independent of the space-time point, you really recover the previous theory that you'd get out of regularity structures. So in that sense, it's a strict generalization of what you could do with regularity structures, or at least this meta theorem before. Okay. How am I going to do that? Well, let me start by reviewing what's known. So if I had to do everything from scratch, this would be a very hard problem. Thankfully, actually, many of the ingredients were already in the literature. Essentially, this becomes another instance where the hard part is the probabilistic part, though at least the remaining open part was the probabilistic part. Why is that? Well, this adage that at the PDE level, changing the differential operator doesn't hurt you too much turns out to also be true at the level of the solution theory. So if you open Martin's original paper on regularity structures, modulo very minor changes because the assumptions on the kernel are a bit too stringent, you can basically get a solution theory for these variable coefficient operators, assuming you're given an appropriate model, out of what he already did there. The thing you lose is that the description of how you renormalize, so the kind of algebraic machinery that sits at the back end of regularity structures, at least if you use this, the paper of Ivan Brunet, Lorenzo Zambotti, and Martin Heyer, that doesn't work anymore once you're in the variable coefficient setting. So you need to use an alternative framework that is a bit more flexible. And it turns out there's already a good candidate in the literature. So Ivan has this kind of nice recursive approach via preparation maps. And with Ismail, he proved in 2021 that this algebraic description is sufficiently robust to allow non-translation invariance. So you can give a kind of algebraic description of renormalized models that tells you how the kind of term-by-term renormalization translates to a renormalization at the level of the PDE. I want to note, though, that that's not the same as saying that you know how to get local counterterms. So they don't give you a prescription that says if you renormalize in this way, you'll get a local counterterm at the level of the equation. They just tell you how to translate the renormalization you do for the model to the equation itself. So the open question is it possible to build a renormalized model in such a way that this paper would yield you local counterterms so that you can kind of plug it into the solution theory that you would get from here. And it turns out the answer to that question is yes. So this is what I was able to prove last year with Luca and Harpreet. So roughly speaking, the result says the following. If you give us smooth and uniformly elliptic coefficient fields, and you give us kind of a nonlinearity and a driving noise that are such that any of the translation invariant BPHZ results would apply, if I were to take this triple to just be a triple of constants, then we can exhibit a sequence of models on the usual regularity structure associated to this nonlinearity, which are associated to local counterterms and that converge to a non-trivial limit as epsilon goes to 0. So this is exactly what you would want from a BPHZ theorem in regularity structures. What I want to then do is maybe, okay, I admit this is not a short paper, so I'm not going to be able to give you a summary of every detail of it. I want to give you, though, some idea of first how you would go about trying to identify where you would get local counterterms, and then maybe a very high level overview of what goes into the proof. And I think by then I will be kind of out of time because I think I have roughly 10 minutes left, right? Something like this.
That's right. Yeah.
Yeah, good. Okay, so first let me try to tell you a little bit how you might in these problems find local counterterms. And I want to do, again, one of the simplest possible examples, maybe here even simpler than the parabolic Anderson model. Let me start with just 542. So in 542, there's a very obvious way that you might go about trying to treat the variable coefficient problem. You might try to do the de Prato-de Buch trick, which would mean you kind of formally write your solution as the solution with just the kind of driving noise, ignoring the nonlinearity, plus a remainder, and hope you can solve the equation for the remainder. In order to do so, you'll need to make sense of some nonlinear functionals of that solution. So kind of, I guess people may well know that you need to make sense of these two, usually Wick products. If you use the Wick prescription for renormalization, that essentially corresponds to subtracting off a constant that is the expectation of your, for example, renormalize your square, now evaluated at the point z, because I don't have translation invariance to see that this doesn't depend on a space-time point anymore, because this is not a translation invariant kernel. Unfortunately, it turns out that's actually not the right thing to do. So it's not so hard to see that this Green's kernel G depends in a relatively complicated way on the coefficient field. So it certainly doesn't depend in a way that's local. Furthermore, inside of this kind of integral, I'm integrating over at least one of the points in my Green's kernel. So I'm very likely, and in fact it is true, integrating also over the coefficient field. That's already true in this very simple example where the tree is what we would usually say is associated to a local counterterm. If you look at 543, things get much more complicated because you'd have this tree where you would integrate over this variable, and that makes things even worse. You're kind of certainly integrating over the coefficient field here. So if you want to get local counterterms, even in the most simple example of the 542 equation, you have to work a little harder than just using the kind of naive Wick prescription in order to define your renormalization. How can you do that? Well, you need to know more about the Green's kernel of your differential operator. Thankfully, we actually know quite a lot about these Green's kernels. So one way to construct them is via these kind of parametrics methods. So you make a first guess, maybe by freezing coefficients. So that's kind of what's written down here. This is just the heat kernel with coefficient A of W. And okay, this guess, of course, turns out to be wrong. If you plug it into the operator without frozen coefficients, you get an error, which is what's written here. But it's known that this error actually, when you convolve with it, improves regularity by 1 degree. So subsequent terms in this kind of sum are more and more regularizing, and this is, in the end, enough to prove that this kind of series converges and gives you a Green's kernel for your variable coefficient differential operator. Why is this helpful? Well, in the case of the 542 equation, I mean, this is barely diverging, right? It's a logarithmic divergence. So as soon as you get anything more regularizing, you're going to have no problems. In particular, as soon as k is 1 or more, since you gain a whole degree of regularization, you're actually not going to contribute to the need for renormalization. So the only way in this kind of parametrics decomposition of your heat operator that you see a need for renormalization in the case of 542 comes from this first term where k equals 0. Here you have a very good way of freezing in coefficients because you can isolate all of the dependence on the coefficient field in one variable, and you're left behind with something that's actually a translation invariant kernel. In general, you might need to go further into this expansion, and then this kind of simple phenomenon is not any more true. But you can work a little bit harder. So since this is all very explicit and you know how the differential operator depends on the coefficient field, you know how Z depends on the coefficient field, you can kind of iteratively in this expansion, Taylor expand in the coefficient field in order to write it in a similar form to this W, where you have one variable that's the dependence on the coefficient field and another variable in which your translation invariant, up to a remainder that is as regularizing as you like. So up to a remainder that won't contribute to the renormalization, and therefore that you can throw away. Why is that helpful? Well, it suggests that in order to solve this variable coefficient BPHZ problem, you can actually pass to a much simpler setting. So rather than trying to construct this renormalized model on the kind of complicated variable coefficient structure, you can instead give yourself the problem of constructing the model that's associated to these frozen coefficient operators for every base point in which you could freeze. And this is, okay, it's in some ways a more complicated problem because it's in some aspects infinite dimensional, but from the perspective of proving BPHZ theorems, it's also simpler because now you only have to work with translation invariant operators, and therefore you can hope to use the kind of machinery that we developed before again. Okay, one thing you could do is you could try to run the spectral gap proof at this level. I think though that would be overkill. Much simpler is to note that by some kind of functional analytic, let's say magic that I don't have time to explain, it's enough to think of the case where on every edge of your tree, so for example, let me think of this tree I drew in 5, 4, 2, I have a specific kernel frozen at some base point, and these might be different base points. And then it's not so hard to cook up a usual regularity structure with for a constant coefficient system where this tree would appear. So the fact that your constant coefficient BPHZ theorems are so general actually already tells you that you have all of the stochastic estimates for this variable coefficient problem. Just by cooking up the right systems of constant coefficient equations, you can kind of go from the top to the right system and thus the right regularity structure, and then you can apply whichever BPHZ theorem you want. So the diagrammatic one or the spectral gap one, and that will tell you at this level you have the right stochastic estimates. What's then the kind of hard part, the why wasn't this done before? I mean, it's in some sense non-obvious how you go from this frozen coefficient problem back to the model that you're actually interested in, where the coefficients are unfrozen. In some sense, though, this is actually very similar, I would say, to the problem you faced in spectral gap. Why is that? Well, when you replaced your full Green's kernel with the frozen coefficient kernel, you're in some sense building a very good approximation to the Green's kernel around a frozen base point. So you have a good local expansion of the kernel. Since regularity structures is a kind of analytic machinery for understanding exactly the errors you make in these local expansions, you might hope that this model, where you've kind of unfrozen the coefficients, can really be recovered by the machinery of regularity structures, so by the reconstruction theorem, from the kind of models that you see here. The question is then, what's the right kind of analytic object, so what kind of bounds you need on the coefficients, in order to really make it true that you can get the model that you want here as the reconstruction of some model distribution against the frozen coefficient model that you built here. And it turns out that's exactly the same kind of machinery that you needed in the spectral gap proof. So in the spectral gap proof, I viewed the Malievan derivative as a model-like object that I wanted to construct in a quantitative sense from a model that I was already given. Here I can view equally this renormalized variable coefficient model as a model distribution, even one of the same kind of model distributions, now in an L-infinity-based topology against the kind of frozen coefficient model that I have here. Of course, there are lots of complications that I hide. So for example, integration at this level gets fairly complicated when you try to recursively construct these model distributions, because there's quite a big difference between the variable coefficient integration here and the constant coefficient integration here. But it turns out that that's something you can do. So with Luca and Harpreet, we, amongst other things, made sense exactly of this arrow using the same kind of analytic machinery that came out of the spectral gap proof. So in some sense, the summary is that along the way in these spectral gap proofs, what I would like you to take away is we didn't just learn actually that spectral gap is a useful quantitative tool when constructing renormalized models. We also learned that there are very good analytic tools, which are the kind of tools that you use in the solution theory for regularity structures itself, that can be used in the problem of constructing renormalized models. And those are useful more generally than looking at this kind of constant coefficient problem via the spectral gap inequality. And as a first kind of proof of concept, we already use them to construct renormalized models at the same level of generality as the constant coefficient setting, now with variable coefficient operators. Yeah, okay, but maybe let me kind of stop there. So there's lots more detail I could say about this paper, but I don't maybe want to go into that because I'm very nearly out of time. So let me stop. Yeah, let me stop there, and thank you for your attention.
All right. So let's thank Rhys for that nice talk. And yeah, open the floor to questions.
Rhys, how well do you think this approach can be applied to if the operator is made non-local?
That's a good question. So I'll be honest, I never thought about this before. So probably whatever answer you get from me is you should take with many grains of salt. I mean, I would. So, I mean, the kind of input question that I would need the answer for is how much I know about the Green's kernels of these differential operators. In some sense, the thing that makes this local variable coefficient proof work is that I have very explicit descriptions of the differential operator and a very natural way of freezing coefficients. I'm not an expert on non-local operators, but I would guess that's not something I know in that setting. And if so, it would be very difficult to apply these techniques. This thing I did with Luca and Harpreet is really built on the fact that you have a natural way of freezing coefficients. So you could hope to apply it also to non-translation invariant noises, but I don't know for non-local operators if it really would say anything. But that might be just I don't know enough.
Thank you.
Yeah, any other questions? I had a question which is so this is, I guess, what you've described now kind of gives you a very robust local theory. Is the picture clear enough to where you could do stuff like coming down from infinity for 5-4 with non-translation invariant stuff? Or I mean, is that clear, or are there some kind of major obstructions there?
So I would hope that there are not major obstructions. So actually, I mean, one of the very important things that we wanted in this work, like you could imagine that once you have this frozen coefficient structure, you could try to build the whole solution theory up here, right? With respect to the frozen coefficient model. And actually, I think we basically have all the analytic ingredients modulo putting in like time zero boundaries to make that work. The reason we didn't want to do that is that then when you try to do exactly these things like coming down from infinity or kind of more generally kind of global existence for things like GPAM, which now people can do very well, it would be much harder at this level because somehow your local descriptions are much more complicated. And so the hope is that somehow the description that you get down here is sufficiently similar to the one that you would get in the constant coefficient setting that all of these results should apply. There is kind of a caveat. So at least depending on which proofs of, for example, coming down from infinity you read, one very important tool is looking at the equation convolved at a certain length scale. And so it's very important that the convolution commutes with the differential operator in those approaches. That's not true in the variable coefficient setting. So there are at least some kind of pitfalls, but those I kind of suspect you could, okay, we didn't try to write it down, but I'm pretty sure that they should be kind of minor technical difficulties, not really anything essential. And I don't even think it would be all that difficult. I would hope it would be straightforward.
Okay, that's great. Yeah, any other questions? All right, so if, there are no more questions, let's thank Rhys again. and I believe this is probably going to be our last meeting for this summer. Yeah, have a good summer, and we'll begin again in the fall. So thanks everyone, and thanks again, Rhys. Yeah.
Yeah, thank you for